Lesson 8.6 is the last lesson in Unit 8, and what we're going to do here is really not anything new. We are going to instead compare the three big function families that we've studied this whole year. So now that we know the primary and most important characteristics about quadratics, we're going to compare them to the linears that we did in the fall and the exponential functions that we did late fall as well. So we're going to be able to, at the end of this lesson, decide from the equation, from the graph, and from a table whether a function belongs in the linear family, the quadratic family, or the exponential. And let's start with the equation because that's probably the easiest way. Equation and graph, I think, are going to be fairly comfortable. You know, it's stuff that we've done before. The one that might be a little bit different, that's actually a new concept or topic, is the patterns in a table. We've talked about the patterns in a table for linears and exponentials, but this is really the first time we're going to talk about what patterns to expect when we're looking at quadratics. So let's go ahead and begin. Linear functions. So we know it's a linear function when the equation itself can be simplified to y equals mx plus b. That b might be a 0 and might not be present at all. But the idea is if we do all the simplifying, if we do all the math we can do and combine like terms, and we're left with something very simple, just an x term and possibly a constant, and there are no exponents kind of in the mix here other than the implied 1, then you know you're dealing with a linear function. Okay, so the big things here, just to make a note, write these down, are no exponents. And you know that I mean other than 1 because the 1 is kind of implied. That's a degree 1 term. So that's another way to think of it. It's linear if it's a polynomial that is degree 1. Okay. And then from the graph, you should be very, very familiar. You did this for, several years at this point. All linears graph to be a straight line. It never changes direction. It doesn't curve. So those are the primary characteristics when we're working with linear functions from the equation or the graph itself. Okay. Then we've got the quadratic. Of course, this is the one that we introduced recently in this Unit 8. For the quadratic function, when you're simplified and in standard form, x is always squared. And you can think of it as a degree 2 polynomial, right? So, and when we look at the graph, it is that, so we call it a parabola, but it's that U-shaped curve, right? So U-shaped curve that we've been studying so much over the last couple of weeks. Okay, and I'm going to go ahead and add, I do think it's important. So basically this is a degree 1 polynomial, and this guy is a degree 2 polynomial, if that helps, right? All right, so we know those characteristics because we've been playing around with them a lot. Now we know that these guys can come in point slope, slope-intercept, and standard. We know these guys can come in intercept form, vertex form, or standard. So we really are looking at sort of that simplified version where all the math is done. Okay, and then the last one that we talked about, this was around the November-December time, was the exponential functions. And what really characterizes them as exponential is that x is in the power. So it's not a polynomial because the variable is not your base, and then you have a degree. The actual variable is the exponent. So x is the exponent. Okay, and we know that for these graphs, these are one-sided curves, so they're not symmetrical like the parabola where it's identical on both sides. This is a one-sided graph or curve, and if you recall, one side grows really fast, the other side approaches the asymptote. So these are the ones that introduced us to the concept approaches the asymptote. Okay? That's that number that it gets closer and closer to, but never quite reaches. All right, so equation, graphs, I think we're good here. So what's really a little bit new is the patterns in a table for a quadratic, which is really not something that we've talked about. We've talked about the patterns or the differences on a table if we have a linear or exponential, but we're going to want to know what it looks like for a quadratic so we know what to look for. So you can use patterns between those consecutive, meaning they're one right after the other, data pairs to determine what type of function models a set of data if it's given to you in a table form or as a set of ordered pairs, for example. So the differences of consecutive y values are what we call the first differences. So if those consecutive values, if we subtract them, and that difference between them is what we call the first differences. This is what's new today. The difference of the consecutive first differences are called the second differences, okay? So you're like, what? And when you see it in action, it's going to make more sense. But this is really the only new information today. Everything else is sort of reviewing and bringing together things you already knew. But this concept of the second difference is really what is new and different in today's lesson. So let's just do a quick review. Linear functions always have a constant first difference. So that means that on the table, when we compare the y2 minus y1 over x2 minus x1, that rate of change, if it's the same every time on your table, then you know you have a linear. Okay. Exponentials, we look at consecutive y values and we check to see if they have a common ratio. So linears, it's first difference. Exponentials, it's a common ratio. That's when we are checking if we divide y2 over y1, do we get the same constant number every time? Okay, so of course the big difference is quadratics, or the new topic is the quadratics. And the fact that quadratics will always have a constant second difference. Okay, so what does that mean? You'll see in a moment when we do tables, but basically we're going to take the first differences, and then once we have those first differences, we're going to do it again. We kind of, that's kind of a new column, if you will. Then we'll take the differences of those. So the second differences are the differences of the first differences. Sounds very wordy. It'll make sense when we see it on tables, okay? In all of these cases, and this is important, okay? In all of these cases, you want to make sure that the x values are going at a constant. It doesn't have to go by ones every time necessarily, but it needs to be at a constant rate. So x should be going up by the same number every time. And if it does, then we can trust and look at the patterns in the y values and make decisions of that. Okay, so let's do a quick review, and then we'll really focus on the tables in just a moment. But because we haven't done this in a while, let's graph some points and decide if we can determine if it's linear, exponential, or quadratic. So I'm going to go ahead and whip up a graph here, and it looks to me like the majority of these x values are negative. So I'm going to scoot my y. These are the kind of things that, as a pro, which you are getting to be, y'all, you can start making those decisions. Look at your data and adjust. That's why we give you a blank canvas here, so you can adjust the axes to fit your data best. Okay. So I saw all my x's are negative. However, all my y values are positive, so I don't need to put this in the middle. I want to capitalize everything, basically as much of this third quadrant, which I bet you is where these the majority of these points are going to be. Okay. So we'll graph this guy right here. We'll plot those points, and just based on the shape of this graph, we'll make a decision as to which of these families this graph belongs to. So let's go ahead and plot these points. We've got a point at -3, 2, which is right here. We've got -2, 4. 1, 2, 3, 4, right there. We've got -4, 4. So 1, 2, 3. That was not at 3. Hang on. I'm so silly sometimes. Let's try this again. 1, 2, 3, up 2. That's much better. And then we had 1, 2, up 4. Then 1, 2, 3, 4, up 4. So right away, this is not going to be a straight line. This is not going to be a one-sided curve. We're going to finish out just to be sure, but I have a feeling we already know what this is going to be. If we do -1 and up 8, so 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5 to the left, and up 8 there. If we connect these guys, I think we are pretty confident that this makes a nice parabolic U-shaped, and then we can conclude that this is a quadratic. It definitely meets the criteria for a quadratic function. There it is. Okay. Let's graph this guy here. So I have negative, 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 positive, positive. So I've got some negative, some positive x values. But on my y-axis, these are all positive y values. So I'm going to drop this all the way down. I don't need any negative values, which is typical a lot of times, not always, but in an exponential, especially in Algebra 1. So I'm really just going to, I do have a little bit more negatives than positives, so I think I'm going to maybe just scoot this over like this. Just a little bit off center, give myself a little extra room on the left. Let's go ahead and plot these points. So we've got the point -1 and then up 4. We've got -2, +2. I don't know why I started here in the middle, but then I've got -3, up 1. So far so good. And then we've got 0, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then 116, which is definitely not going to fit. So, but it's going to be pretty high up there. So 3, 1, 2, and then 4. Okay, good. So we've got something that basically looks like this. Based on that, the data, the points that we have and so forth, we are looking at an exponential. So I'm looking at something that looks like this, a one-sided curve, grows very quickly. And then we could check that, right? We've talked a little bit about this a bit. If I did the ratio, 2/1 is 2, 4/2 is 2, 8/4 is 2, 16/8 is 2. So I can see that there's a common ratio that makes this definitely be exponential. Okay, so just a little review there. Plotting points, looking at the characteristics of the graph, and determining what kind of graph that might be. Let's go ahead and just do one more. I'm going to skip over to number 4. Maybe I'll have you guys try number 3 on your own. And then let's talk about number 4. So number 4, again, the majority of my x values are, well, actually 2, positive, negative, negative. Yeah, the majority are negative. And I do have y values that are both positive and negative. So I'm going to keep this kind of right in the middle. Let's do that. Might scoot this over a little bit. Give myself some more room. Like this. I think I forgot my arrows on the last graph. How dare I? Okay. Proper graphs are important. All right, let's graph this guy right here. And we've got the point 2, -4. So over 2 and down 4. 2, 3, 4. So we're down here. Then we have the point 0, -2, which is right here. Then we've got -2, 0, which is right there. That's my x-intercept. And then -4 up 2. And last but not least, -6. 1, 2, 3, 4, 5, 6. Up 1, 2, 3, 4. And I can see here that, especially, I'm looking at them like it looks pretty straight. If I put a straight edge up to that, it most definitely fits the bill of a straight line. Okay, and we know that there's only one type of function that will make a nice straight line like this one, and that is your linear function. So this guy is a linear function. Okay. So just a little practice there. You should have that in your notes. Let's go on to what we really want to talk about. You know, it's going to be those tables, right? So whether they give it to you in a table or they give it to you in a set of ordered pairs, it's really the same idea. We want to make sure that we can identify what kind of family function it comes from. Always check to make sure your x values are going by a constant amount. We're not going to really throw that curveball at you, but in the real world, you want to make sure that that is the case before you really proceed here. Okay, so let's take a look at number 5. So we've got constant here, and then we have our data here. The question is this linear, exponential, or quadratic? So being able to tell from our answer, from our work. Now, normally what I do is if I see like things seem to be kind of going at a fairly steady rate, I might start with checking a linear. If I see that it's already growing in a very disproportionate, very large rate, I might start with a test for an exponential. But I think testing for the linear is probably the best first step. So what I want to emphasize is that what I'm about to do is what we were referring to earlier as the first difference. So I'm about to take the first differences of my data. Okay? First difference is basically the difference in the original data points. So if I go from 7 to 4, that's a decrease of 3. Or in other words, 4 minus 7 is negative 3. Okay? If I test this one here from 4 to 1, that is also a decrease of 3. Or in other words, 1 minus 4 is negative 3. So you can always do y2 minus y1 and get the same answer if it's not obvious by looking at it. Same thing here. If I go from 1 to negative 2, that's a decrease of 3 again. Or in other words, negative 2 minus 1 is negative 3. So again, y2 minus y1 is continuously giving me the same constant answer. Last but not least, negative 5 plus 2 is negative 3. Remember, I did plus because it's a double negative. Or in other words, from negative 2 to negative 5, this decreased another 3. So this is the first difference, which is the difference in your original data, and it was constant all the way down. There's only one function family that has a constant first difference, and that is your linear. So this is a linear function, okay? And that's called the first difference. Now let's go ahead and try number 6. Number 6, we look at it, we're like, okay, let's go ahead and check it out. Now you might already be able to tell just from the data, but I'm going to show you what we're going to do here. We're going to do the same thing again. These don't look like they're growing astronomically necessarily, at least not yet. So I'm going to do exactly the same. I'm going to start by checking out that first difference, which is the difference in your original data values. And so from 2 to negative 1, that is a decrease of 3. Or in other words, y2 minus y1 would be negative 1 minus 2. So that works. Okay. Right here, my next difference here from negative 1 to negative 2, that's only a decrease of 1. So that already tells me it's not linear, unless I made a mistake, but I didn't. But that doesn't mean I'm going to stop, because one of the tests that I'm about to do is then second difference. So I got to keep going and continue this work, okay? From negative 2 to negative 1, that actually goes back up. It's a positive 1 there. It's an increase of 1. And then from negative 1 to 2, that's an increase of 3, okay? If I do y2 minus y1, I get 3 there. So definitely not a constant first difference. So I am, if I'm kind of like crossing out and eliminating, I can already eliminate linear. This is not going to be a linear function. However, what I'm going to do now is, since it didn't pass the linear test, is I'm going to go on and test for the second difference, which is what we want to check for to see if this is quadratic. So I'm literally just going to do the same thing again, but to this row. So this is what we call the second difference, and it is a difference of the first differences. Okay, so instead of original data, I'm now going to see how did these guys change. So from negative 3 to negative 1, that is actually an increase of 2. Okay. From negative 1 to positive 1, that also increased 2. And from 1 to 3, that increased 2. So there's my second difference, and in this particular problem, the second difference is constant. That does come out with the same constant second difference every time. And that, my friends, is the new information in today's lesson. That is what makes it a quadratic. There you go. That's a quadratic function right there. Okay. Now, if you tested the first difference and it was not the same number every time, you went on to check the second difference, you still did not get the same number every time, then that would rule out quadratics, and then at that point you might want to test to see if it's exponential, okay? So let's try this one here. Again, I'm going to start with that first difference. That's usually how we start, although I'm going to do this for the sake of our notes, but you might already see that this grows a little too fast to be linear, but again, it could be quadratic, so you still want to do the first difference so you can then test for the second difference. So we're going to do this one a little bit faster. We know how to do this y2 minus y1. So this increased 1, that increased 2, that increased 4, and that increased 8. Definitely not linear. So now we're going to check for the second difference and see if this is quadratic. Okay, so I'm going to check the difference of these differences. So this went up by 1, this went up by 2, this went up by 4. So also not constant. So quadratic is out. Okay, so then we have to throw that out and be like, oh, okay, what else can we check for? Oh, yeah, we can check to see if there's a common ratio, and in that case, that would make this exponential. So for a common ratio, what we're going to do is we're going to test, we're going to go back to the original data, right? These guys did not work. So we're coming back to the original data, and we are going to test the ratio of y2 over y1. So like here, y2 over y1 would be 2 over 1, and that just simplifies to a 2. 4 over 2, y2 minus y1, over y1 here, that'd be 4 over 2. Hey, that also simplifies to a 2. Okay, let's try the next one. 8 over 4, what is 8 over 4? Oh, yep, that's also a 2. And just for good measure, we'll test the next one. 16 over 8, we can already see 16 over 8 is also 2. So in this particular case, this is the one that has the pattern, is that common ratio, which makes this data exponential. Okay, there you go. So this is your strategy or your plan of action or plan of attack, if you will, to decide. Okay, flip that over. It's really going to be the same if you have a set of data points. In fact, there's really no difference except the format that they've given you this data, in this data, okay? So what we are going to do is we're going to just try a couple of these and see how this goes. But what I might recommend, I feel like the data, even though it's the same idea, it's a little easier to see when it's in a table format. So I'm going to do a table format for us here. Doesn't take very much to just rewrite this as a table. That might make it easier. If you don't think it makes a big difference, then you don't have to do that. But I've got my x values here are -2, -1, 0, 1, and 2. And then the -2 is paired up with a -4, -1, 2, 5, and 8. And I don't know about you. I think that this makes it a lot easier for me to work with this data. Just make a quick table of these values. And then the rest of this work becomes exactly what we did a moment ago. So try this one. Go ahead and press pause and then see if you can determine what function family this actually belongs to. Okay, hopefully you got linear on this one, and it is linear. That first difference is already constant. You're good to go. Try number 9. Let's try that. And again, make yourself a little table of values. That might help organize things here. You got that -2, -1, 0, 1, and 2. And then for our outputs, we've got -9. We've got 0, 3, 0, and -9. Okay. So now like I said, you might already see some of the hints. You might be able to actually see the symmetry happening in your table if you get the right data. If you happen to be lucky enough that your vertex is kind of in the middle here, you could sort of see the mirror image or the symmetry in your data. That's okay. I'm still gonna have you show your work, of course. You know me. But you can already, for example, maybe avoid doing the ratio first and jump into this difference because you have a feeling that it might be quadratic, right? So again, we'll find these first differences. This went up by 9. This went up by 3. But then from 3 to 0, it went back down by 3, and then it went down by 9. So obviously the first difference is not constant. So now we will test the second difference. So the difference here and here and here. So from 9 to 3, that's a decrease of 6. From 3 to -3, that's a decrease of 6. From -3 to -9, that is a decrease of 6. So in this particular one, we are looking at a quadratic for sure. Now, I just realized something. They also want us to write the functions. So let's back up a second. I went a little too fast. It says decide if it's a linear, exponential, quadratic, but then write the function. Yeah, we should have done that, right? So let's come back to this guy. Let's back it up. So quick review, right? We know that linears are going to have this form where m is our slope or our rate of change and b is our y-intercept. Okay, so we're kind of lucky enough here that, you know, we can come up, we already know what the difference here is, and we know that the slope is always the change in y over the change in x. So here it looks like our change is 3 every time that x goes up by 1. So change in y over the change in x, so our slope is 3 over 1, or in other words, just 3. The other good news is that our y-intercept is right here at a glance. Otherwise, we could find it, but we can see here that the y-intercept when x is 0 is 2, so that gives us our b value. So this one's not too bad. We can just go ahead and write our equation here. It's got a slope of 3 over 1, or just 3, and a y-intercept of 2, and that is a function or the linear. And you can put this in your y equals and pull up the table of values on your calculator, and it should match what they have up here. Okay, this guy right here is going to be a little bit more of what we're doing now. It wants us to write the linear equation. Okay, now let's take a look at what we know. Now, I could use vertex form, I could use a few things, but what's really jumping out at me is that I look like I have the intercepts right here already, for intercept form. Right, so those are my two, those are like my P and Q. Okay, so I can actually borrow that and then some other random point perhaps, and put this into intercept form. So that's what I'm going to go for. And then I can, of course, rewrite it in standard. So because I have the intercepts handy, though, I'm going to start, and because we just did this lesson, I'm going to start in this format right here, okay, where I know that my P value and my Q are those intercepts, which are 1 and -1. So if I just put those guys in, it would look something like this and like that. However, that's not enough. I need A. So now I can grab any of these points that I haven't used yet, the -2, -9, the 0, 3, the 2, -9, and borrow them to find A. We've done this before. I think I'm going to pick the middle one, just for fun. So I know that y is 3 when x is 0. So I'm going to put that in there. I think the math will be pretty easy for this one. If I do 0 plus 1 is 1, and 0 minus 1 is -1, so I get 1 here and -1. And 1 times -1 is just -1. So I end up with just A times a -1 is equal to 3. And if I just divide by that, I find out that A has to be -3. Now I can write my function in intercept form. So our function, if I were to just leave it in intercept form, would look like this. However, that's a 1. Okay. However, I'm pretty sure they're going to want standard. That's usually like our go-to. Okay, so all I have to do is multiply this in, do a little FOIL here, distribute the 3, and we're in standard. Remember, standard is just a simplified version of these. So let's finish it out with that. This is a difference of squares, so if you catch that, you can save yourself some time. Told you guys, those things will come in handy. So that's a difference of squares, x plus 1, x minus 1. If we multiply those together, whether you FOIL it or you realize it, you're going to end up with just x squared minus 1. The middle terms are going to cancel. And then we distribute that -3. So our function in standard form is just this guy right here. Ta-da! So this one's quadratic, and that would be the function. And I think we're going to stop here. We will leave number 11 as one that we do in class together, but they're really just asking you to tell what data this particular table represents. So we'll do that one kind of as a warm-up in class.